Okay, thank you for tuning in to this video as part of the 2021 Sagan workshop. My name is Lynne Hillenbrand. I'm a professor of astronomy at the California Institute of Technology, and I was asked to speak to you today about how we determine the properties of young stars from the observational perspective. And I should say that there is a complimentary talk on this topic by Isabelle Baroff, who's speaking on the theory. As well as sessions during the first day, talks by Tom McGath, Jonathan Gagne, and a live panel that we'll have with Baroff and myself, Greg Feiden, and Chris Johns-Kroll. So I encourage you to tune into that for some discussion of these issues. So what I want to speak to you about today is how we know what we know about young stars. First of all, what we want to know, what we can observe, and what we are able to infer from the observed quantities, as well as how reliable any of this is. And I'm trying to keep in mind that the conference is in the context of disks and planets, so particularly young objects, typically pre-main sequence, though for more massive stars, young main sequence objects as well. And some of the questions that are going to be asked during this conference are issues associated with how properties of disks might correlate with, say, the mass of the central star. And so we'll have a lot of talks on disks, as well as companions or planets to stars of various mass and age. And quoting here a slide, the previous time I gave a Sagan talk was about 7 years ago, and the conference there was about direct imaging. And so I had a long full hour on just how we determine ages of stars. And so some of the parts that I will go light on here were covered there. The basic story hasn't changed, though the data, of course, are much better now. So you can look back at that if you want more, particularly on main sequence ages, let's say. I will touch on that towards the end. And so a common question then is, what is the faint thing that I've detected near my bright star? And is it a brown dwarf or a planet? So these are two common questions that I think we'll see during the week. And so I want to start at the most youthful phases. And again, I'll refer you to the presentation by Tom McGath, who will speak solely about this topic. So at the very youngest stages, we believe we have an accretion and outflow system. And so these are fairly complicated. The young star down in the center has a fairly complicated circumstellar environment. It's both acquiring material from the disk and ejecting it along an outflow axis. And that's shown in this simulation here. And so there are various things that we can observe. Some of them are probing the circumstellar environment, and some of them we're hoping to see directly down into the central stellar object itself. And one of the things that spectral energy distributions, and these spectra go from ultraviolet wavelengths all the way out through infrared wavelengths, mid-infrared, far-infrared wavelengths, millimeter wavelengths. And what is shown here are different, from the work of Tom Robitaille, are predicted spectral energy distributions for different kinds of circumstellar dust geometries that are given in these symbols in the upper left. And so for any given geometrical distribution of dust and gas around a young star, there are many possible different spectral energy distributions that might emerge depending on some of the other parameters and the radiative transfer. So there's a modeling unit, hands-on workshop as part of this conference that the students will be engaged in that will help you appreciate some of the subtleties of this spectral energy distribution modeling. So what we observe is flux as a function of wavelength, and what we hope to infer is both information about the circumstellar structure, but then also in the very simplest case shown here in the upper left, these are stars, all of the same luminosity, integrated flux under the curve. But what we're seeing here is a distribution of SEVs based simply on the temperature of the source. And so SEVs are insight, at least at the youngest stages, into what the stars and the circumstellar material might look like. Conversely, for any given object, so this is from the same Robitaille paper, for any given source that has an observed SEV, so that's what's shown as the points or upper limits across the figure, for any given observed spectral energy distribution, there are a number of different geometries that could fit with the right scaling of the other parameters. And so SEDs themselves are quite degenerate. But again, you'll get experience with that. What I'm here to tell you about is basically how do we determine the properties of the underlying star, because these models, of course, rely on both the underlying stellar source, which is essentially the light bulb in what you're seeing here, as well as what is going on with the accretion and radiative transfer of that stellar plus accretion luminosity through the circumstellar structure. So what I want to know is, what can we learn about the central object? The little black point is symbolized in all of these subpanels of this figure here. So how is it that we can learn about the star? If we zoom in, so look now in detail at the very inner regions of this disk, what's shown here is kind of our standard paradigm for a rotating star with a strong magnetic field that is able to hold off the disk material from which is accreting inward. So mass is moving inward, angular momentum is moving outward in these disks. When material gets to this inner part of the disk, it can be redirected into an outflow. It can accrete onto the central star. And so there are lots of observations that we can take of very young stars that help us learn about the accretion outflow process. But again, what I want to focus on is how we know something about the central star itself. So empirically, spectra might look like this, and going from bottom to top in this figure, we're increasing the accretion rate. So the mass of material moving in through the disk and landing onto the central star. So generally what we're observing in these optical spectra is the flux that emerges as a function of wavelength for material that's crashing along this magnetosphere into the stellar photosphere, merging with the stellar photosphere essentially. And so there's a range of properties. As we increase the accretion rate, we move from a spectrum that looks like, in this case, a fairly normal late type T-Tauri star. And as we increase the accretion rate, we see more emission lines, more continuum excess or veiling that fills in the spectral lines. And I'll talk more about that as we go on. There are, of course, lots of emission lines, as I said, and we use them mainly to infer something about the accretion process, either this infall region, rotation of gas in a disk, or about material being ejected in the outflow. And again, it's not necessarily the topic of this discussion. However, it's an important aspect, something we need to overcome in order to learn about the properties of the central star itself. So there are various observational aspects of taking spectra of young stars, and we need to separate the circumstellar and the stellar influences. So if we now look around the galaxy, there are many, many star-forming regions to study. This is the glimpse scan along the inner part of the galactic plane. So this goes from about minus 60 degrees in longitude to plus 60 degrees in longitude, and scanning right through the galactic center. And you can see there are many, many star-forming regions to study. Gaia has, of course, enabled us to figure out the third dimension and how distant many of these regions are from the sun. Distance is, of course, an important parameter for learning about the central stars themselves. And so I want to spend a little bit of time discussing, just as an example, and showing some recent results studying the stellar population in this region. Just an example of one of these star-forming complexes. This is Cygnus, which is actually out at about 90 degrees away from the galactic center. But Cygnus is a fairly large star-forming complex. There's a piece of it over that I want to concentrate on here called the North America and Pelican Nebulae, which is an H2 region powered by essentially a single O-type star is illuminating this H2 region. But there are thousands of stars, lower mass stars that have formed as part of this complex. And so this is a couple of degrees on a side. And if we zoom into that region a bit, so here's now a scale bar, so it's showing 1 degree, we can look at the stellar population here. And this is from an analysis by Michael Kuhn. And the different colors indicate different groups that can be kinematically identified using Gaia data. So with Gaia, we get parallaxes, which enable us to infer distances, as well as proper motions, and enabling us to look at the kinematics. So the arrows here are indicating how these stars individually are moving. And so what has been possible now from these kinds of studies is to determine the membership of these star-forming regions. So that's an important process, as we want to find the young stars one way or another. So Gaia has been an excellent resource complementing past techniques of looking for infrared excess objects, ultraviolet excess objects, emission line objects, variable stars. All of these are proxies for youth, but really being able to kinematically identify the members of star-forming regions and open clusters and moving groups. All of these have really come to fruition in the past couple of years. So it's been amazing to see our new appreciation of stellar populations in these various regions. But what we can do with this information, just as a general statement, is to compare the stars that are being formed to the properties of the gas. So these are showing different intensity and velocity maps of the gas, so we can map what the molecular cloud is doing compared to what the stars are doing, and look for correlations that enable us to infer something about the star formation history in this particular region. And one of the things that we can do is look at the expansion times for these different subgroups. So again, these are kinematically distinct subgroups, and they can be studied in terms of how rapidly they're expanding. And we want to look at things like the total mass in the cluster versus the mass in the gas, and so on. So again, all of this is only just recently possible. We can take it one step further by now comparing kinematic information. So these are now the same subgroups shown in this plot. So the color scheme is the same between this figure and the next one, which is simply indicating the groups on the sky and various members. These stars have been studied in also a recent paper led by Min Fang, where we've been able to take thousands of stars across this several degree region and collect spectra for them, and use the spectroscopic information in conjunction with the Gaia information to look at what the HR diagrams, how the HR diagrams appear. And that's what I'm showing in the upper left panel here. For each of the different subgroups has a different panel in this HR diagram, and the median run of luminosity with temperature is shown as the blue line. And so there are pre-main sequence evolutionary tracks here. And again, I'll refer you to the talk by Isabel Baroff, who explains in detail what the physics that goes into these tracks and what they're predicting. But basically the stars contract towards the main sequence, first along convective tracks for solar type stars, let's say, and then along radiative tracks to reach the main sequence, whereas low mass stars fall simply straight down the tracks along convective tracks. And so if we look at the blue line, which is this run of effective temperature, a run of luminosity with effective temperature, we can see that it's not exactly aligned with tracks. So this is one of the issues in inferring stellar properties, is the current mismatch between the pre-main sequence evolutionary tracks and the empirical sequences in these young clusters. So I'll come to that. But what I want to leave you with here is the point that the goal of these kinds of studies is to infer something about the star formation history in these molecular clouds, how the stars, how the groups are expanding, and these will turn into what are later seen as moving groups in the sky. So once the gas is gone, these stars still retain some memory of how they formed and as they expand into the galactic potential. So we can decipher, this group is one of the older ones, and this compact group C and this compact group E, which is where the deepest, darkest part of the most dense part of the molecular cloud is. These groups are the youngest, E and C, and group F is the oldest, with these others kind of intermediate. And we infer that basically from the relative luminosities in the HR diagram for stars that are essentially all at the same distance. There are small differences in distance between these, but essentially at the same distance. And so the relative position in the HR diagram gives us some information about the age. Now, the other thing that you'll notice from these diagrams is that there is quite a lot of scatter, and that is something that has been apparent in HR diagrams for many decades. This luminosity spread and what it actually means in terms of star formation histories. And that's been, as I said, topic that has been discussed for quite some time. What is interesting to me here is that these HR diagrams that I'm showing here have been constructed from a very careful vetting of the membership of the cluster. So we've tried very hard to constrain the sources to only those that are members of this cluster. Done a very careful job, as I'll show you, placing them in the HR diagram. And then we still have this rather large luminosity spread. So stars do not lie along, a single isochrone, 1 million years, 2 million years, 3 million years, and so on. But they're spread across some range of corresponding ages. And so what that actually means is still a topic of discussion. So I'll come to all of this. But just finishing up on the kind of very young cluster part of this, there are a number of questions. I won't go through all of these, but the reason we study these young clusters and try to understand the properties of the stars is, we are still developing our understanding of cluster formation and dispersal, and then issues such as the initial mass function and how stellar multiplicity arises and what the multiplicity properties are. So, and I think the thing of most interest to people at this conference is the planet formation processes, how planets form and the timescales on which they form. And those timescales, obviously there's theoretical work, but also a lot to know from the empirical perspective, which relies on age dating the stars. And so addressing all of these questions requires some understanding of the properties of the stars. So let me get on with things here and try to walk us through some of what we're trying to do when we study young stars. So as I've already said, we now have this wealth of parallaxes from Gaia, which can be for nearby regions more or less directly translated into distance, which is amazing to know the distance to many of these classic star forming regions and individual isolated stars as well. So Gaia has been a lot of fun for many people. And the other thing we know are about positions and proper motions, also from Gaia, which lets us do the clustering and kinematic analysis that I was just talking about. We also measure photometry. There are many wide field surveys now, all sky, over multiple wavelengths from the ultraviolet to the mid-infrared. And those help us establish the spectral energy distributions that I was showing earlier of young stars and stars of all types, in fact. But for the young stars, the spectral energy distribution, and in particular the infrared excess, tells us about the dust disk. And particularly if we know something about the underlying star, we can then infer better the properties of the circumstellar material on the disk. Also through photometric surveys, there are many time domain surveys now. So repeated observations of the sky from optical to near infrared to mid-infrared wavelengths, as well as other targeted surveys outside of those wavelengths, but those are the main ones. And so those, when we watch sources vary in time, that's teaching us about the changes in physical processes that manifest as changes in radiation. So we both learn about dynamical and radiative processes by studying photometric variability. And then spectroscopy is, as is often said, is where the real physics is. So when we're able to obtain spectra of these young stars, particularly focusing on the star itself, we can learn something about the temperature and the gravity. We can measure radial velocities. If they're variable, they can imply some multiplicity, either binarity or planetary companions. We can measure rotational velocities from spectra. We can also measure composition, which is a little bit more involved. So regarding the star itself, these are the main things that we're after. We also learn from spectra, as I discussed earlier something about the accretion and outflow processes by analyzing the kinematics of spectral lines. So spectra are quite rich in what they're able to tell us. So what do we want to know then, based on what we measure? One of the primary things I think is age. So that's clearly a topic of high interest. How old is that disk? How old is that planet? How do stars evolve? So we need ages to reliably interpret how our evolutionary tracks our theoretical evolutionary tracks are behaving. And so we would like to understand, for example, how stars gain their mass. So how do they acquire mass through the circumstellar disk? How do they evolve in luminosity as a function of time, effective temperature as a function of time, and radius as a function of time? I think this one is particularly of interest to this group because much of our planet detection techniques these days are through transit techniques where the radius of the star is important. We want to understand the mass of the star if we're looking at radial velocity measurements of planets, for example. So these are important quantities to be able to know or infer. How does the mass radius relationship evolve as a function of time? So again, if you want to understand stars, right, these are processes, the processes that cause these evolutionary changes are things that we would like to be able to measure and compare to the theory. We also want to understand ages because there's a question of how the disks evolve, in what manner circumstellar disks accrete onto the central stars and evolve to form planets. How do the planets themselves evolve? Both their radiative processes, just like stars. Planets acquire mass, they accrete mass, and they evolve in luminosity, temperature, and radius over time. So just like we want to understand these things for stars, we would like to understand the youthful phases of planets as well. And then planets also evolve dynamically within a planetary system or a debris disk system, and we would like to understand that. So ages are critical for deciphering some of these properties. And my prediction is that as this conference goes on this week, there will be many plots shown where there's some quantity plotted as a function of age. And what I would like to caution everyone is that these ages are uncertain, and people will tell you that, and it's something that we're still working on calibrating the believability of ages of stars. And so my suggestion is that you look at stars basically, almost all of them with at least a 20% at best, and for young stars, more like 200% errors in their ages. Okay, but besides age, of course, we want to characterize the basic properties of stars. So that includes temperatures, masses, radii, and luminosities, as I've said. And some motivations are listed here for the why we would want to understand this in the context of disks and planets. So these are the fundamental things that we try to determine when we observe stars, particularly and especially young stars in this case. And there are other stellar parameters that we'll discuss briefly a bit later, and other speakers will touch on as well. So returning now to the HR diagram. So these are just basic isochrones that are plotted 1 million years, 3 million years, 10, 30, and 50 million years as the black line, which is not necessarily the main sequence as we go to these very low mass stars. As I hinted earlier when we were discussing the stellar population in the North American nebula, these theoretical isochrones do not yet match the empirical sequences of luminosity as a function of temperature. And so there's that issue, and then there's the spread in luminosity that I also have discussed. However, the HR diagram is our most important tool because it is something that we can, with some work, create these HR diagrams, which for young stars, particularly stars in star-forming regions, we do need to operate in the space of luminosity and effective temperature. It's very hard to operate just in, say, an analogous color magnitude diagram, because we have extinction, we have contributions from ultraviolet excess and infrared excess, and so on. So yeah, the HR diagram is really the place that we would like to operate for analyzing young stars. So this slide is simply an illustration of the different, some of the different sets of tracks that are circulating. And the point here is that there's, you can see in the talk by Isabel Baroff, there's still uncertainties, particularly in the convective region for low mass stars, which are fully convective. So once stars turn onto their radiative tracks, many of these models are in fairly good agreement. So in this particular representation, the black lines are the same among the different panels, and the red sequences are various other models that are being compared. And you can see there's some differences, but at young ages and low masses, there's still differences between these tracks, and that's where observations can most help us sort these things out. Okay, so this will go by very quickly. So if you're interested in deciphering this, you can pause the video and take a good look. But I just wanted to provide a flow chart for how we wind up, or how we go about putting young stars in the HR diagram. So, we start with some photometric measure. So it could be a full spectral energy distribution, or it could just be one magnitude and a complementary color. Ideally, we would like some information on the disks, the influence of accretion on the photometry and the spectroscopy, and a spectral type so that we can determine the temperature. So the spectral type, if we do it correctly, can lead directly into a temperature. And we combine the spectral type, then usually forms the basis. So on the one hand, it gives you the temperature, which is the x-axis of our HR diagram. On the y-axis, we have to figure out how to calculate a luminosity, and that's basically the standard steps that we all learned in undergraduate astronomy classes of how this goes. But for young stars, it's particularly an issue because we do need to account for the extinction towards the source, and we need to account for any circumstellar influence, as I said, on the photometry or the spectroscopy. So the influence of the disk complicates this, but otherwise it's the straightforward process that you would use to put any star in the HR diagram. So we want to determine the reddening. So once we have the extinction towards the source, we can correct our SED or our photometric magnitude with a bolometric correction applied to it, so that we measure the full or infer the full luminosity of the underlying star. The distance is obviously a key parameter here, and derive a luminosity in this way. From luminosity and effective temperature, of course, the radius comes right out. And if we combine that L and T with premium sequence isochrones, like I've been showing, we can infer something about the age, and the masses come from the contraction tracks. So again, these stars are all contracting towards the main sequence as a function of mass. So the higher mass stars take a shorter amount of time, the lower mass stars take a longer amount of time. The sun is about 30 million years. The lowest mass stars, kind of just above the brown dwarf limit, are hundreds of millions of years. And of course, there are errors in all of these processes. And so they range from observational errors, systematics, and the scales that we use to translate spectral types to temperatures, the intrinsic colors that we adopt, the reddening law that we adopt, right? So there are assumptions that go into this. So there's some systematic error, and the luminosity inherits errors from everything that comes before, obviously. And then, as I've also mentioned, there are differences in tracks. So there can be systematics in ages from using one set of tracks versus another set of tracks. So back on this diagram, if you choose one of these sets of tracks, there may be shifts in the mass scale or the age scale, depending on the physics that have gone into that set of tracks. Okay, so just to be a little more pedantic about this, so here are some spectra. So on the top, optical spectra, on the bottom, infrared spectra, and so these are late type stars. These are high surface gravity main sequence standard stars to which we might compare our young stars. And so some of these spectral features, molecular features in this case, TIO, are sensitive to temperature. And then others where we're comparing here main sequence, the same main sequence standard as over here, but younger stars, so 5 or 7 million year old stars, and 1 or 3 million-year-old stars, there are changes in some of these spectral lines, both molecular and atomic, as a function of the surface gravity of the star. So this is an indicator that something would be naturally expected to be above the main sequence and a young pre-main sequence star. Similarly, in the infrared, we have some features are sensitive to the temperature of the star. So as we go to later types, they're cooler stars have more molecules. And similarly, there are certain lines that are sensitive to gravity. And so these are just two snapshots in two different parts of the spectra, but across the blue to red optical and near infrared, there are various temperature and gravity indicators that are used together to get to determine the spectral type of these young stars. And if we take a lot of spectra and make an HR diagram for a star forming region, so I showed before the very young North America Nebula region, which is still embedded in lots of molecular gas and dust. This is now an older region, the SCO-SEN complex, where what I'm showing here for each of these are subgroups in upper SCO. So the story is this is the youngest, this is the next youngest, and this is the oldest of these subgroups across the SCO-SEN region. And what I'm showing here in the upper panel versus the lower panel is the change that comes essentially from using Gaia. So in the upper panel, the stars are placed in the HR diagram, assuming basically the same distance for all stars, and including all candidate members that have been identified from the literature. Whereas in the bottom panel, the sample is restricted to be only sources that meet the kinematic association with the cluster. So cleaning it up for having the right parallax, having the right proper motion to be part of the cluster. And that doesn't necessarily, there can be interlopers, right? Stars that are not kinematic members, but fall as interlopers with the same kinematics, but not quite, not actual members of the cluster. But the point is, you can see as we go from the top panel, the dispersion in luminosity as a function of effective temperature decreases from the top panel to the bottom panel. So we've sort of cleaned up the HR diagram, and that's true for each of these three cases. Now, these are a couple of years old, so there's been a lot of work more recently, particularly filling in the low mass populations in some of these other more sparse groups. So this exercise needs to be redone, but I'm merely showing it as an indicator that when we clean up the membership list by using Gaia and use this region is close enough that individual distances, so parallaxes for each star that has a parallax have been used in this exercise. And so the luminosity spreads that we saw in the North American Nebula, as I said, they have had the same kind of vetting, but they were even worse than the 0.3 to 0.4 dex luminosity spread that I showed before. And in this case, I can illustrate here the difference. So the main point that you want to note here is that the lines on the top panel, which are basically the luminosity spread from the upper HR diagrams in each of these three cases, are higher than the lines here. So the luminosity spread, when we do a good job vetting the cluster membership, does decrease. So again, Gaia is enhancing, just knowing the distance and understanding the membership is key for a lot of advances that we're now seeing in the area of stellar young stars and cluster membership and understanding the properties of these young stars. So these errors now get down to the point where we can explain the luminosity spreads, almost, not entirely. There's still a little excess error here, but this is indicating what we could expect the dispersion to be if stars have some fraction of them are binaries. And so the luminosity spreads are getting down into the range where we can say that they're acceptable for these stars that have some amount of accretion activity left, particularly in the upper SCO region, but not a lot. So these are stars that should be fairly clean, right? The disk fraction is low, the accretion rates are low. And so we would expect them to be able to be well placed in the HR diagram. So we want to test, at least test our methods and our knowledge in regions like this, and then go back to this North American Nebula region and try to try to understand, how we really get the stellar parameters for the truly young stars. Okay, so the point here is that it's not quite as easy as just applying the flow chart and making HR diagrams. So when we go back to then the younger stars with some amount of accretion, we have activity, both the kind of underlying active stellar photosphere is active on its own, but then there are also accretion effects. As I've said, the stars have gas and dust surrounding them, and so that complicates how we de-redden them, how we place them in the HR diagram, what wavelengths are best for deciphering, what's coming from the star versus what's coming from the disk. And so where we actually do that, should that be done in the optical or the near infrared as a function of spectral type of star at all? These are still technique questions. There's no necessarily best way, but the main point that I want to convey is that people do need to be aware that the disk does influence how we spectral type stars and de-redden stars. And then the other thing that I want to touch on as we go ahead here is the complication of variability. So all young stars are variable, all stars are variable, but particularly young stars are photometrically variable at some level. And the variability is larger in the optical wavelengths with a mean of a few tenths of a magnitude in optical wavelengths, and then decreasing as we go out into the near infrared and the mid infrared. And this is the influence of, again, the accretion and the disk activity is not a steady state process, right? There's variability that comes from that. There's underlying variability that comes just from the spottedness of the star. So I'll touch in a few slides more on some details of this variability, but it is a complication for how we place stars in the HR diagram. And so one might think that we should survey long enough to determine the median magnitude of a star, and we shouldn't just take a single measurement, right? But we should figure out what's the typical brightness as opposed to how bright it was on the day we happened to take our photometric measurements. And then I'll come back to these issues a little bit later, but for stars that are fading, should we use the bright state photometry? For stars that are undergoing bursty type accretion, should we use the faint state? So these are all questions regarding how we should really be putting these stars in the HR diagram. So this is just an illustration of this is a oldie but goodie figure that I still like. So this is showing a photosphere, underlying photosphere, and an observed spectral energy distribution showing that for at least some of these systems, there's excess emission at all wavelengths. And so if we wanted to put the star in the HR diagram, the luminosity that we care about is this underlying photospheric luminosity, but what we measure is up here. And so unless we have some accounting for the fact that there's some excess accretion, we can be mistaken. We can, in this case, we would have an excess luminosity compared to the stellar luminosity in our HR diagram. And then again, this is just illustrating how this accretion luminosity, particularly out in the ultraviolet and into the optical wavelengths, does vary as a function of time. And so do we use this flux? Do we use the minimum flux that we have observed to put the star in the HR diagram, because that's most close to the stellar photosphere, as opposed to this flux, which is measuring more of the accretion. So again, issues to consider. These figures are back again to this North American Nebula spectroscopic survey paper led by Min Fang, so the illustration here now is how can we account for these accretion effects when we perform spectral typing of young stars? And what is shown here, so these are 4 spectra, all of the same object, and different. So from each of these spectra, we can try to infer simultaneously both the underlying spectral type as well as the contamination, the filling in of spectral lines due to the accretion process. So that's what we call this veiling parameter. And so what's shown here on the right-hand side are a green versus a red spectrum, where the green is an unveiled spectrum and the red one has a little bit of this accretion activity added. And so you can create these contour maps essentially, so that give a probabilistic estimate for what the spectral type of the star is and what the veiling is at the same time. And so you can see, I mean, it's hard to see maybe in this representation, but if you look at this in detail, you will see that the red line better matches the observed spectrum for this particular star than the green line. The green line is too deep. The lines are not that deep because they're being filled in by accretion. And so if we account for both the accretion and the temperature and try to fit for them both at the same time, we can do a good job deriving both of those parameters. In contrast, the star on the bottom, which again has 3 separate observations, and they all tell us, more or less consistently the same thing, that it's kind of an M2.5 star. Here, the red line is not the right fit, the green line is the right fit. And so the lines are deeper, there's no veiling for the star. And so we can just get a nice kind of a one-dimensional spectral typing the traditional way without accounting for veiling. So again, this is just highlighting the importance of fitting for both of these parameters when we're placing stars in the HR diagram. And so this plot is showing what spectral type would be derived without the veiling versus the spectral type that is derived with accounting for veiling. And as expected, there's sort of a systematic effect where if you don't account for the veiling, you will infer a temperature that's too hot, a spectral type that is too early. So again, the veiling is kind of filling in the spectral lines. So it makes us think it's an earlier spectral type than it is, particularly for the late M-type stars. And so that's shown here. So this veiling affects the temperature axis, and then as one would go through the flow chart in how to make an HR diagram, how to construct a stellar luminosity, if you propagate this systematic effect on the spectral type into the luminosity, what you find is that it causes a scatter in the luminosity. It's not as, it's a systematic shift in the temperatures, but it causes scatter in the luminosity because there's an effect both on the bolometric corrections one applies, the intrinsic colors, as well as and therefore the extinction. So you can get both an increase and a decrease in the luminosity by not accounting for veiling. And so we can get a scatter here of about 0.15 in these in these luminosities if the veiling is not accounted for. So again, that's a good number to keep in mind as we look at age spreads in the HR diagram. So we can get a scatter of a few tenths of a dex in luminosity by not accounting for the veiling. Okay, and then the other, so coming now to this point of stellar variability and how does that affect how we determine stellar parameters. What is shown here is the amplitude of the variability. So going from very small, a few hundredths of a magnitude variability, a tenth of a magnitude RMS scatter in time series photometry to 1 magnitude of variability, which is quite large, but there are objects that have that significant amount of variability. So this is plotting the amplitude of the variability as a function of the magnitude of the star. And so the gray here is the field star population. So sort of stars as a function of magnitude that may or may not be young, just field stars towards, again, this North America nebula region. So for stars that are members, so the member stars that are placed on the HR diagram are colored points here. So for stars that have variability essentially within 1 sigma of the mean, so the mean variability for stars as a function of magnitude is the black line. For stars that have variability that are members within about 1 sigma of that, this is the HR diagram. So it's about 30% of the sample. Then an intermediate case, and then the high variability objects that have more than 2 sigma variability are plotted down here. That's about half the objects. So again, young stars are intrinsically variable, in part because of the accretion and in part because of high activity in spots. And so what's interesting here is that the scatter is actually not, compared to the blue line, the scatter is not significantly different as a function of variability. So that's it's a little bit surprising to me. So the high variability case, yes, does have a fairly high spread in luminosity, but the low variability case, has essentially a comparable spread in luminosity. So I was a bit surprised by this. So again, it's telling us that the veiling effects are systematic. The variability, which is essentially some kind of random scatter in the inferred luminosities, it's actually not not affecting the placement or the scatter in the HR diagrams very much. So this is a little bit of a surprise to me. So again, sort of a similar 0.3 dex scatter in the luminosity. Okay, so let me say a few things about now coming to the nature of this variability. And again, I am not talking about the mechanisms or causes of the variability itself. This is fascinating work, the details of this. I just want people to understand when we're placing stars in the HR diagram, we are picking a magnitude, and stars vary about that brightness or magnitude. And so some of them are bursty, like this one, or like all of them on this panel. Some of them are have this kind of quasi-periodic enhanced brightness, though by factor of 2 in this case. And so if you observe a star here for your HR diagram placement, you'll get a different luminosity by a factor of 2 than if you observed it in kind of this low state. So again, that's the this is the detail of what the stars are doing, whereas in the previous figure, it was simply an RMS value that was being plotted. So this is in detail what the stars are doing. And so in these cases, the stars, in the cases where what we're seeing is variable brightening as material falls inward and lands on the star is the translation of what we're looking at here. In these cases, we would think that the right place to use for HR diagram placement is this low state, right? We wouldn't want to be putting stars on the HR diagram. In this case, the source is a factor of 5 or 7 brighter than its median state down here. So this is the right place. But if we have a random observation, we don't know if the star was flaring, bursting versus in a low accretion state. So conversely, there are light curves that look like those on this panel. And in this case, the idea is that what we're seeing is variable obscuration of sources. And these come in, again, different timescales, different amplitudes. But the idea here is that if you could see, that maybe the right place to place the star in the HR diagram is at the high state, and that these dips or fades are temporary increases in extinction. And so unless we get the extinction at the same time that we're calculating the flux, you kind of want the bright state here for the HR diagram placement. But again, a random observation, we don't quite know exactly what state the star is. So again, this is illustrative only as a complication for the variability aspects influences on the HR diagram. Okay, so the good news is that the variability amplitudes decline with age. And so this is a plot made by Louisa Rabol from K2 surveys of various young regions and clusters that she has studied for the purpose of determining rotation periods. But this is simply plotting along this axis the amplitude of the variability. And so at these very young stages that we've been talking about, 1 or a few million years, you can see that the amplitudes are typically above a tenth to up to 1 magnitude. For kind of typical variability of young accreting sources that look like this. And then as stars age, they still have, we lose the accretion influence, the accretion aspect of the variability, but they're still variable because of the spotted nature of the stars. And so, and this will come up, I'm sure, in many other talks in this conference, particularly when we're looking at transiting planets and an influence of spots and our ability to detect them. So the amplitudes go down, the variability go down as a function of age. So again, it's easier if we wanted to place stars in this age range in the HR diagram using the techniques I've described. The luminosity spreads are much smaller than at these younger ages. Okay. And of course, all young stars are variable, and the pre-main sequence stars do stand out. And so, variability is useful in part as a way to find these young stars. Okay, so the issues that I've touched upon so far include, I don't mean this to be too much of a skeptical talk. The HR diagram is the best tool we have for deriving these stellar parameters. So radii, masses, and ages, despite the uncertainties that exist. They're still the best tool that we have. And it's just the fact, the thing I want to emphasize is that we just need care when placing young stars in these diagrams, and be particularly pay attention to how we interpret the information that we get from HR diagrams. So there are spreads in luminosity, right? The cluster sequences are not very tight at young ages, and there are a number of possible contributors to this. But as we continue to explore them, photometric variability, the aspects of accretion, the depth of clusters, as we continue to look into these, it continues to be hard to make these luminosity spreads go away. So there's something about the accretion physics is probably some answer to this. And so the other aspect of this is the empirical. I didn't illustrate this very clearly, but the fact that the isochrones the empirical isochrones tend to cross the theoretical isochrones does tell us that there's still some missing ingredients. And as I said, it's currently thought to be issues with the accretion history of the star. One important way that we can check on these models is to measure mass and radius directly. And so I'll just very quickly illustrate how that's possible. And so the same way one finds transiting planets, there are eclipsing binaries that stand out in these beautiful K2 and now TESS light curves. So this is just highlighting some work that was done by Trevor David earlier to identify some of these very young systems. And so from the light curve, you figure out the radius ratio from a velocity curve. You figure out the mass ratio, or sorry, it's M2 over M1 plus M2. And combining these infer fundamentally the masses and the radii to quite high precision for these double line eclipsing binaries. So again, these are stars where you need to see, they need to be close enough in mass that you see the light to model the radial velocity curve. It's not a single line spectroscopic binary, but actually a double line spectroscopic binary. So this is a necessary selection effect that they tend to be fairly equal mass, the systems that we can study well. But there's a premium on these systems because if we look instead of the HR diagram, so instead of luminosity and temperature, we plot radius. So in the pre-main sequence phase, luminosity decreases as a function of time because the fundamental thing that's happening is the star is contracting, right? The mass of the star in a post-accretion phase remains the same, but the radius is decreasing as it approaches the main sequence. So fundamentally, radius versus mass is a much more fundamental diagram. But what I want to illustrate is that there are a few more systems that one could place on here now, but this is essentially
it's 3 o'clock.
It's essentially the run of such systems that we know about that have been well studied. And so in particular, what's highlighted here are double line eclipsing binaries in young clusters. So there again, we think we know an approximate age for these various clusters. And what's apparent here is that the isochrones that are predicted, so these are lines of constant age is what's plotted here. The eclipsing binaries actually do fairly well, the observations and the theory match fairly well in this plane of radius versus mass. It's pretty good. This is a much better isochrone than you get for upper SCO in luminosity versus effective temperature in the HR diagram, say. So the theoretical calculations of radius as a function of time and radius here plotted as a spread out by mass, these are working quite well from the theory side. But as I said, if we put these same stars in an HR diagram, we get much more of a systematic mismatch between clusters of a given age and how the stars appear in L versus T. And one way of fixing that is to shift the models cooler by about 150 or 200 Kelvin so that they would better match the data. And this is widely discussed in the literature. I don't want to spend too much time on it here, but there are pre-main sequence evolutionary tracks that include the effects of spots or the effects of magnetism. And here I think we'll be discussing some of this in our panel discussion talks during the first day of this conference. So we'll look at that there. So there are other observed properties of young stars, and I think I'm running out of time to be able to give you any less than a whirlwind or any more than a whirlwind tour of this. but besides the fundamental aspects of the properties that we've tried to look at so far, so temperature, luminosity, radius, mass, and the all-important age. Some other things that we can measure include rotation rates of stars, which is a interesting subject in and of itself, of how stars, what the rotational history is as a function of evolution towards the pre-main sequence and the spin down on the main sequence. Young stars are active because they're rotating rapidly. They're magnetically active as manifest in coronal and chromospheric activity. We can measure magnetic fields directly for some stars. And again, that's something that will come up during our panel discussion. And lithium is an important element that can be measured for very young stars and helps us with the clock and age dating in some cases. So these indicators can be used as proxies for age, with appropriate caution, because there's a lot of scatter at the very youngest ages, and then things do settle down into some nice sequences for older clusters. The main advantage of these couple of measurements and interpretation of these measurements is that they do give you diagnostic power in the HR diagram once stars reach the main sequence, and they are then not changing their luminosity and temperature as a function of age, but just sitting there, and we don't really know how old they are. Some of these things, indicators, can be used as proxies for age. Okay, so I'm going to transition the talk. I've not too much more left, but I realize I'm over time, so thank you for continuing. I'm not going to talk about HR diagrams anymore, so if you want to cut it short here, that's great too, and hop on to the next talk. But I'll tell you now, just remind you that as these stars are evolving in the pre-main sequence towards the main sequence, as a function of mass, as we go up the HR diagram to higher mass stars, we have different interior structures of the stars, the lowest mass stars and the intermediate mass stars at very young ages, and all of the low mass stars are fully convective for some portion of their early evolution. The higher mass stars then turn on these radiative tracks to approach the main sequence. So there are changes in the internal structure of the star, and that's illustrated in this plot here. So this is showing radius as a function of time. So the stars are all contracting at young ages. The lower mass stars take longer to reach their equilibrium radius on the main sequence. The higher mass stars reach this equilibrium main sequence radius a little bit earlier, and then in this case are actually starting to evolve off the main sequence after a few billion years. Again, it's both the interior, the overall radial collapse, but the differences in the radiative and convective zones in the interior of these stars that give us different evolution of the angular momentum, and that's what's shown on the right-hand panel. It's just the angular velocity as a fraction of the critical velocity, and showing how stars contract. They contract and they're spinning up as they hit the main sequence. When they're on the main sequence, the winds carry angular momentum away, and the stars start to slow down. And so empirically, we want to try to map this. And so there's a series of papers by Louisa Rebull and other groups also working on this general problem, trying to map the rotation, so rapid rotators here, slow rotators here, as a function of color in this case, for different clusters as a function of age. And you can see that when the young clusters are kind of a mess. There's a wide range of rotation rates, and it's tied up in the evolution of the circumstellar disk, for example. But as we get to these older clusters, these sequences, nice rotational sequences, develop. And so the idea is the stars contract as they approach the main sequence, and then slow down, so move gradually upward in this plane as they age. And there's a rough mass dependency of this evolution. So this is another version now extending out to somewhat older, somewhat different set of clusters. Some of them are the same, some are new clusters on this plot. But basically, for the higher mass stars, we do have a rotation age dependence. The lower mass stars seem to retain this tail of rapid rotators even out to quite old ages, right, approaching a gigayear. They're still quite rapid rotators at the low mass end. And so the idea is to try and continue. This is where K2 has contributed, but now TESS is also bringing in rotation periods for many hundreds of new stars across the sky. And what we need is the information from Gaia and other diagnostics of cluster membership to really make sure that we're including only member stars in these clusters and continue to map rotation as a function of age for clusters of known age. And then what's shown in gray here in this plot from a paper by Jason Curtis is the field star population. And so, we would like most field stars are old, right? Not young, but we would like to be able to map the rotational spin down of stars as a function of mass and better calibrate these rotation age relationships. So again, this is a proxy for age. It's also the case that there's surface activity, right? So in addition to the rotation, rotation causes, rotation is the fundamental thing, but there are manifestations of that having to do with the magnetic field and surface level activity. And then again, we see different things in different places of the HR diagram. So in the low mass, fully convective regime versus as we go to higher mass stars, can be a different relationship with the stellar magnetosphere. And so there are different probes of activity. And again, I'm not going to go through all of these, but there's X-rays, ultraviolet. So X-rays probing the coronal magnetic reconnection in various ways. The ultraviolet, both continuum and chromospheric lines, which are also seen in the optical, tell us quite a lot about the temperatures of the chromospheres, and in this case, showing some evolution from higher to younger to older stars. This is, of course, the sun in an active versus an inactive state, and so this combination of activity on stars of different age, or stars of different stars of different age and clusters help us develop calibration tools for inferring ages of field stars for which we don't have a better way of getting at their age. And so these are some figures just randomly taken from the literature where people try to do this. They take the chromospheric activity, the coronal activity, the rotation, and try to infer some from some age activity indicators, try to infer the probability that any particular object has a given age. So there are two different examples of this. So people have been doing this for a while. So the data are improving, and the number of stars for which we want to apply this is, of course, increasing as we now have more of these, many more rotation periods, many more planets. There's a premium on learning, trying to constrain the ages of these stars. So again, once the stars are on the main sequence, we don't have these premium sequence tracks, but we can use these proxy indicators to try to get at a probabilistic age for the star. And finally, another measurable is the magnetic field, and this is just showing a recent figure, again, a pre-main sequence HR diagram showing various stars for which magnetic fields have been measured. And you can see for the lowest mass stars, so these are, again, the fully convective stars down in this low mass regime, the magnetic fields are fairly large. And again, our panel discussion, I think, will touch on these issues a little bit more. But again, enhanced magnetic fields are a feature of these pre-main sequence stars. They're higher than what we think obtained for main sequence stars. Okay, so that has been a whirlwind tour through stellar properties of young stars and how well we might be able to constrain from what we can observe, how well we might be able to constrain more fundamental parameters like masses and radii and ages of stars through various observables and proxies. And I'm looking forward to learning about all the exciting developments in circumstellar disks and young planets that we're going to see this week. So thanks for tuning in.